geometry of the unseen. To understand the fourth dimension, we must first acknowledge the limits of our own biological hardware. We are three-dimensional beings inhabiting a Cartesian universe defined by the orthogonal axes x, y, and z. Every location we can touch is a coordinate on this grid, but mathematics proves the existence of a fourth spatial vector, the w-axis, which exists perpendicular to all three known directions simultaneously. The build-up to this hyperobject follows a rigorous geometric logic. We begin with a zero-dimensional point, a position with no magnitude. Extending that point along the x-axis creates a one-dimensional line segment. This is one dimension. Think of a dimension as a direction. One dimension, one direction. To add a second dimension, you double the line, and you connect the line by two perpendicular points, creating four vertices. Now you can move in two separate directions, left and right. This is a two-dimensional world. Translating that segment perpendicularly along the y-axis introduces a second dimension square, bounded by four edges. Lifting that square into the z-axis, this is done by replicating the square and connecting the corners together in a three-dimensional cube, a volume bounded by 6 square faces. To build a cube, we must arrange these 6 squares into a specific configuration on a two-dimensional plane known as a net. The most recognizable version of this net is the cross, or the lowercase t shape. In this layout, all 6 squares are connected by shared edges, which will eventually act as hinges. It takes the form of the cross, or a lowercase t shape, the fold rotating into the z-axis. The transition to 3 dimensions begins when we designate one square as the base. Then we perform a series of orthogonal rotations, folding the adjacent squares 90 degrees away from the flat plane. The walls. We fold the 4 squares surrounding the base upward. At this moment, the two-dimensional edges of the squares meet in three-dimensional space to form vertical vertices. The resulting three-dimensional cube, or hexahedron, is defined by 8 vertices, the points where the 3 edges meet. It is the perfect rigid body structure. Every angle is exactly 90 degrees, and every face is equidistant from the opposite. When we rotate a standard cube in our three-dimensional reality, we are manipulating it around 3 stationary lines that meet at a single point: the x, horizontal; y, vertical; z, depth. X-axis rotation. The cube pitches or tumbles forward and backward like a gymnast performing a flip. Y-axis rotation. The cube yaws or parachutes, spinning like a top on a table. Z-axis rotation. The cube rolls, turning like the hands of a clock or a steering wheel. Throughout this movement, the cube remains a rigid body. Its internal angles stay locked at 90 degrees, and its edges never stretch or shrink. Our eyes easily track these movements because the cube's volume remains constant. We understand that the back face isn't growing as it comes forward. It is simply moving through our field of vision. The Tesseract, or sometimes called a hypercube, is the next step in this progression. It is created by taking the entire three-dimensional cube and translating it into the w-axis. Just like transforming the square into a cube by doubling the square and connecting the corners, we do the same thing, but this time by doubling the cube and connecting 8 corners. The result is a 4-dimensional manifold composed of 16 vertices, a meeting point of 2 lines that form an angle, 32 edges, 24 faces, and 8 three-dimensional cells. In other words, 8 separate cubes combined and folded into the 4th dimension we can't see to form the 4th dimensional cube, the Tesseract. When we introduce the w-axis, the rules of visual engagement change entirely. In a 4-dimensional tesseract, rotation isn't just happening around a line. It is happening through planes. While the tesseract can rotate on the x, y, and z axes just like a normal cube, its most hypnotic motion occurs when it rotates into the 4th dimension, the xw, yw, or zw planes. In this animation, you are seeing a 3-dimensional perspective projection of this 4-dimensional movement. Because our eyes cannot perceive the w-axis, the tesseract appears to do the impossible. It turns inside out. As a set of vertices rotates through the w-axis, it moves from a high 4-dimensional depth to a low 4-dimensional depth. In our 3-dimensional view, this causes the inner cube to expand and become the outer cube, while the outer cube appears to shrink and be swallowed by the center. This folding motion is a visual illusion caused by our limited perspective. In the 4th-dimensional manifold, the tesseract is just as rigid and unchanging as the 3-dimensional cube. Its 16 vertices never actually move closer to one another, and its 32 edges never actually stretch. The morphing we see is simply the shadow of a 4-dimensional object turning through a direction we can't point to. It is the footprint of a higher reality stepping through a doorway that we can only see from the side. In this rendered animation, we are witnessing a phenomenon called stereographic projection. Because our screens are 2-dimensional and our eyes perceive in 3 dimensions, we cannot see a 4-dimensional object in its true form. Instead, we see its 3-dimensional shadow. The inside-out pulse you observe is not the object stretching or morphing. It is a rigid rotation through the XW and YW planes. As the tesseract rotates through the W depth, its vertices move toward and away from the 4th-dimensional center. In our 3-dimensional projection, this causes the cubes to appear to swallow themselves, passing through one another in a fluid neon green dance. The vertices with a high W value project toward the interior of the frame, while those with a low W value expand toward the periphery. This animation is further complicated by simultaneous multi-axis rotation. The object isn't just turning, it is spinning through 4-dimensional space while a dynamic camera orbits its 3-dimensional volume. The result is a constant parallax effect that reveals the hyperstructure from every possible angle. We are not just looking at a digital drawing. We are looking at the visual footprint of a mathematical event. The rigid, unchanging geometry of a higher reality projected into a space we can finally begin to comprehend.